This module concerns the photoelectron spectroscopy of diatomic molecules, and we shall learn about the principles of photoelectron spectroscopy in some detail. Secondly, we will learn about the photoelectron spectrum of hydrogen molecule and how we interpret it, and finally, we shall also study the photoelectron spectrum of the nitrogen molecule. Now, you have already studied atomic photoelectron spectroscopy, and you learned that it gives important information about the ordering of energy levels in the atom and the number of electrons in each occupied orbital. So, we will first summarize the salient features of photoelectron spectroscopy. Firstly, in a photoelectron spectrum, a high intensity beam is impinged on the atom or molecule which you are studying. Usually the He1, the helium-1 emission band, which is at 58.4 nanometer is used, and part of this energy of this radiation is used to knock off an electron from the atom, and the remaining part appears as the kinetic energy of the ejected electron and the resulting ion. Now, the ion is much more massive than the electron, and so almost all the kinetic energy is absorbed by the electron. The second point is that a photoelectron spectrum is a plot of the number of ejected electrons versus their kinetic energies. The ionization energies can then be calculated from the positions of the peaks. Using this relation, the ionization energy is equal to h nu naught, which is the energy of the radiation of frequency nu naught, minus E k, where E k is the kinetic energy of the electron, and h nu 0 is the energy of the incident radiation. And the third point we learned was that the energy of the helium-1 radiation, when you convert to electron volts, turns out to be 21.22 electron volts, and this is just sufficient to ionize only the valence electrons. The core electrons cannot be ionized using this radiation because they have very negative energies and they are closer to the nucleus. So, they are very difficult to remove. You require more ionization energy for their removal. To study them, you use X-ray photoelectron spectroscopy XPS or electron spectroscopy for chemical analysis called ESCA. That the ionization energy is the negative of the orbital energy, which can be obtained by using quantum mechanical calculations, and this is Koopman's theorem. And finally, the height of a peak due to ionization from an orbital is proportional to the number of electrons which were there in that particular orbital. So, in this module we shall explore what added information is obtained from PES or photoelectron spectroscopy, this time of molecules. That was for atoms, and now we are going to study molecules. Now, in the case of molecules, there are other ways besides electronic energy that can be changed, and these are the vibrational energy of the molecule. Ion may change its energy. Again, ignoring kinetic energy of the ion, we may write the equation that we talked about as h nu naught is equal to ionization energy plus the energy of the m plus ion that is produced after ejection of an electron plus the kinetic energy of the electron, where E m plus is the change in internal, that is the vibrational energy of the ion. Therefore, photoelectron spectroscopy provides information about vibrational energy changes of the molecule ion. The 0-0 transition from the ground state molecule to the ion does not involve any vibrational energy change and is called the adiabatic ionization energy. It refers to the least energy required to ionize the molecule without adding any vibrational energy. This is obviously the lowest energy transition, and this we have shown in figure, which gives you the principle of photoelectron spectroscopy. The lower potential energy, Morse potential energy diagram is for the ground state molecule. When it is ionized, it may go to different m plus states, and you can see that they have different energies, and there can be also a change in the vibrational energy of the m plus ion. So, using whatever we have learned up till now, we will study the photoelectron spectrum of the hydrogen molecule. Now, as shown in figure, the electron configuration is 1 sigma G2, and since this is a closed shell system, the ground state is going to be singlet sigma G plus. When an electron gets ionized, you are left with an ion which has an electron configuration of 1 sigma G1, and the state now becomes a doublet state 2 sigma G plus. The first line that is observed is at 15.41 electron volt, and after that there are some equally spaced lines as shown in the right side of. You can see that the molecular orbital, you have 2 electrons, 1 sigma G, they are both in 1 sigma G, and the state is 1 sigma G plus, and when an electron is ionized from there, you get to an molecular ion which has a state of 2 sigma G plus, and the first transition is shown here from 0 to 2, which turns out to be the most intense line in the spectrum, which is shown on the left, and then you have other transitions also which are possible, which are giving you the fine structure of the electronic spectrum of the hydrogen molecule. The first line, as we have said, is observed at 15.41 electron volts, and after that you have some equally spaced lines, and they are shown in the right side diagram of figure. These lines correspond to the vibrational spacings of the hydrogen molecule ion, which is produced due to ionization. Now, the bond order in the hydrogen molecule is 1, because when you remove when you have 2 electrons in a bonding orbital, the bond, and none in an anti-bonding orbital, the bond order is 1. When you remove a bonding electron, as in the ion, the bond order will decrease to 1 by 2, that is half, and consequently the bond length will increase. The photoelectron transitions are also governed by the Frank-Condon principle that you learnt about in electronic spectroscopy, and that means that all transitions are vertical transitions. Figure shows that the most intense transition should be from the 0 level of the molecule to the second vibrational level of the molecule ion that is produced, that is the 2-0 transition as observed experimentally. The corresponding ionization energy, that is 15.83 electron volt, is called the vertical ionization energy and is higher than the adiabatic ionization energy, which is the lowest energy required to ionize the molecule without changing the vibrational energy. Here some vibrational energy change is also there, and that is why it is higher, and because of the vibrational contribution. Now, when you observe the spacing between the individual lines, it is 2322 centimeter inverse, which is less than the vibrational spacing in hydrogen, which is 3115 centimeter inverse, which shows that the bond has become weaker in the molecular ion. This implies that the electron is less tightly bound in the ion, as expected from the fact that the electron has been ionized from a bonding orbital, which weakens the bonding in the resultant ion and reduces the bond order. The binding energy of the hydrogen molecule may also be estimated from the photoelectron spectrum. It may be noted that Koopman's theorem refers to the vertical ionization energy. The vertical ionization energy of hydrogen molecule is the ionization energy of a hydrogen atom, that is 13.61 electron volt. And why is that? Because this is the energy 1s orbital of hydrogen atom plus half the binding energy of a hydrogen molecule. Half because 2 hydrogen atoms participate to form a bond. So, we divide it equally, it becomes half. That means the vertical ionization energy is equal to 13.61 plus half EB, where EB is the binding energy, and that means EB is equal to twice into 15.83 that we had obtained experimentally minus 13.61, and this is 4.44 electron volt, which compares well with the thermochemical value of 4.48 electron volt. And also from figure it is clear that if the internuclear distance in the ion is not appreciably different from the molecule, the 0-0 transition would be the most intense, and very few other transitions would occur with diminishing intensity, as we had learnt in electronic spectroscopy. Also, the vibrational spacing would be largely unchanged from that of the molecule. This could happen when the electron is ionized from a non-bonding orbital, because that would leave the bond order unchanged. If on the other hand the electron is ionized from a bonding orbital, the bonding in the ion would be reduced, increasing the internuclear distance. According to the Frank-Condon principle, the vertical transition would end at a higher quantum number with quite a few other transitions which will be observed. Due to the weakening in the bonding, the vibrational spacing in the ion would be smaller than that in the neutral molecule. This is what we had seen for the hydrogen molecule that we have studied just now. And finally, if ionization is out of an anti-bonding orbital, again there is considerable vibrational fine structure, because the bonding is stronger in the ionized state, and hence the bond length is shorter. This situation can be distinguished from that of ionization from a bonding orbital by the fact that the vibrational spacing is larger in that case. So, now we will use this information to study the photoelectron spectrum of the nitrogen molecule, and this is an illustrative example because it verifies the concept of sp mixing. If you remember, we said that up to nitrogen energy level pattern is different, and after that for oxygen and fluorine it is different, and this is due to sp mixing up to nitrogen. So, recall that in this molecule and all other molecules that have fewer than 15 electrons, that is up to 14 electrons, the sigma and pi energy level order is reverse compared to O2 and the bulk of diatomic molecules due to sp mixing. Photoelectron spectroscopy is experimental verification of this. Now, if we refer to figure, the electron configuration of molecular nitrogen is 1 sigma G2, 1 sigma U2, 2 sigma G2, 2 sigma U2, and then you have 1 pi U4 and 3 sigma G2. The ground state is closed shell because all electrons, all the orbitals are occupied, and it is a closed shell. So, it is a 1 sigma G plus state. The 3 sigma G electron, because it is the outermost electron, it is the easiest to ionize. The next higher ionization potential is for the 1 pi U electrons because they are the next easy to remove, and this is followed by 2 sigma U. Ionization leaves a molecule in its cationic state, that is N2 plus with an unpaired electron. 3 bands are observed in the photoelectron spectrum of dinitrogen. The first has an adiabatic ionization energy of 15.58 electron volt, and this is due to the 2 sigma G plus state which results from ionization of a 3 sigma G electron, which we have noted is the easiest to remove. There is very little vibrational structure, which indicates that the 3 sigma G orbital is not deeply involved in bonding orbital, it is not very deeply involved in bonding. The vibrational spacing of 2150 centimeter inverse compared to 2379 centimeter inverse for molecular nitrogen, it clearly indicates that it is a weakly bonding orbital. This is also seen from the equilibrium bond length of the ion, which increases slightly to 0.1116 nanometer from 0.1098 nanometer in the molecule. Now, you contrast this with the band at 16.69 electron volt, which shows considerable fine vibrational structure and a significantly decreased vibrational spacing of 1810 centimeter inverse. That means that the bonding in the molecular ion has become much weaker than that of neutral nitrogen molecule. All these facts indicate that the pi U orbital is a strongly bonding orbital. The bond length also increases considerably by 0.08 nanometer, and it becomes 0.1175 nanometer. And then finally, you have another band at 18.76 electron volt, and it has very little vibrational structure and a vibrational spacing of 2390 centimeter inverse, which indicates that sigma U is a weakly bonding orbital with only a slight decrease in bond length to 0.1074 nanometer. So, there is another point which has to be noted is that the area under the peak for the central band is twice that of the other 2 bands, and this is because the pi bands are doubly degenerate and the sigma orbitals are non-degenerate. So, because of their there are 4 electrons in a pi orbital and only 2 electrons in a sigma orbital, the height of the peak or the area under the curve is twice that for the pi electrons as compared to the sigma electrons. And now we briefly summarize the vibrational data obtained from the vibrational fine structure for the 3 bands and the interpretation. Here sigma 0 is the vibrational wave number for molecular nitrogen, which we have noted is 2379 centimeter inverse. So, the first band is due to ionization from the 3 sigma G orbital and its wave number is 2150, and difference is the ratio of this compared to that for nitrogen is 0.904, and we interpret that this must be a weakly bonding orbital. When the ionization is from 1 pi U, then the nu bar value is 1810 compared to 2379, it is the ratio is 0.761, that means that it is strongly bonding, and in 2 sigma U the nu bar value increases to 2390 and the ratio is 1.005, it is greater than 1. So, it is weakly anti-bonding, and you can see all that we have said here in figure, which shows the photoelectron spectrum of nitrogen and shows the vibrational spacing in various N2 plus states. So, the above discussion validates our MO diagram for nitrogen and proves that photoelectron spectroscopy provides valuable insights into the bonding in molecules and the nature of orbitals involved. So, in summary, photoelectron spectroscopy provides information about the orbital energies in molecules. Sparse vibrational structure indicates that ionization is out of a non-bonding orbital. Decrease in the vibrational spacing of the ion indicates that ionization is from a bonding orbital, and an increase in it implies that the ionization is from an anti-bonding orbital. And as in atomic spectroscopy, the area under a peak or the height of a peak is proportional to the number of electrons in the corresponding orbital.